So we need to devise a systematic way to do these kind of algebra problems and know that we're setting it up correctly each time. Okay, so to do that, we use something called the reaction quotient, which is this letter Q. Okay, so reaction quotient. And the reaction quotient has the exact same equation as the equilibrium constant. However, this little zero right here, that indicates that you're using initial concentrations. Okay, so this is the only difference between K and Q. With K, we use the equilibrium concentrations. And as you can tell from that previous video, it can be difficult to find what the equilibrium concentrations are. Okay. How we start is by using the reaction quotient Q, which has the exact same setup. You can see here it's still products divided by reactants, but now we put in initial conditions. Okay. And here's how we use the reaction quotient. All right. And so I wrote KEQ here, but I meant to write KC. So apologies about that. Let's fix all of those. So the book, an older version used to use EQ. Now it uses C. So I just want to be consistent. So KC. Okay. So if we calculate the value of Q and it turns out to be less than the value of KC, the equilibrium constant. So Q is less than KC. That tells us the system has too much reactant. And we know the system has too much reactant because it's products divided by reactants, right? Reactants are on the bottom. And if Q is less than K, that tells us the reactant concentrations are too large in comparison to the product concentrations. So in this scenario, the reaction has to shift to the right. And what that means when the reaction shifts to the right, that means the reactants have to lose some of their mass. So this, I'm going to put in parentheses, would be a minus X situation. So in other words, we would have to subtract some unknown concentration from the reactants to get it to shift to the right. Okay. So in other words, the reactants will decay. More reactants will react, but the products will evolve. So more products will appear. Okay, so we'll say minus X reactants plus X products. Okay, so now what about the other scenario? What if Q is greater than K? Well, again, because it's products divided by reactants, if Q is greater than K, then that means there's too much product, okay? And then the equilibrium is going to have to shift to the left. It's going to have to shift from the product side to the reactant side. So that means now it's plus X for the reactants, and it's minus X for the products, okay? And of course, if Q is exactly equal to K, then the system is already at equilibrium and we don't have to do anything. So let's see how this shakes out for that example that we did previously. Okay, so we said the equilibrium constant was 16. Okay, and we also said the initial NO2 and O2 concentrations are 0. So because those are 0, if I plug in, 0 times 0 divided by 9 times 12, right? I'm just putting all the initial conditions in here. So you can see right away that 0 times 0 would mean that the Q is equal to 0. And so that's a Q that's less than K. So let's review that again. So if Q is less than K, it's minus X for the reactants and plus X for the products. And we can see that's exactly what we did here. We subtracted X from the reactants and we added X to the products. However, we could have started this reaction with all products and no reactants. So we could have started with, let's say, 9 molar NO2 and 12 molar O2 and 0 molar O3 and 0 molar NO. And then the signs of those X's would switch, right? At least for their respective position, right? This would become 9 minus X, whereas before it was 0 plus X, okay? So we're going to do several example problems momentarily to describe this, okay? So just to kind of summarize this reaction quotient, okay? So if the Q is less than K, the reaction proceeds to the right. And so this is a good example right here in this graph, okay? So if, let's say, we were starting with 0 products, so right there is, let's say, quote, 0 product, then if we're starting with 0 products, we know automatically that Q is going to be 0, and the reaction has to shift to the right. So what we would see is products increasing, right, plus X, okay? And then we would see reactants decreasing, minus X, okay? So then we would hit this regime right here where now Q equals K, and we're at equilibrium, right? So the reaction is done. It's hit equilibrium, okay? So, but now what if we were starting over here, okay, on this side? So now I'll circle this right here, and that would be 0 reactants. I'm sorry, that's very hard to read. So that would be 0 reactants to start with. And because there's, in this scenario, 0 reactants and some amount of products, we can see most definitely Q will be greater than K, all right? And because when we have something divided by 0, it's infinity, right? So that's the situation of Q much greater than K. And so the reaction will proceed to the left. So in other words, now the reactants will in fact increase and the products will decrease, all so that it can achieve this equilibrium situation, okay? So now in the next several videos, I'm going to be going through many different example problems on how we calculate equilibrium concentrations based on this Q.